Hi, welcome to the C3.ai Digital Transformation Institute's weekly colloquium series. Before I introduce the speaker in today's talk, I want to say a few words about the Institute. As some of you may already know, we are a consortium of many universities and industries whose goal is to promote the digital transformation of business, government, and society through the use of artificial intelligence, machine learning, and cloud computing. We have a number of university partners: Carnegie Mellon, KTH, MIT, CMU, Stanford, Chicago, and the Institute is jointly headquartered at Berkeley in Illinois. High performance computing support for the Institute is provided by the Berkeley Lab and the National Center for Supercomputing Applications. The Institute was started with a generous donation from C3.ai and with cloud computing support from Microsoft. And we also have other industry partners such as AstraZeneca, Baker Hughes, and Shell. We have a number of exciting colloquium talks coming up in the next few weeks. Ben Van Roy will talk next on reinforcement learning bit by bit. Devavrat Shah will talk about causal tensor estimation. Simon Nache from Microsoft Research will talk about challenges and opportunities in cloud operations research. Murat Archak will talk about hierarchical control for cyber-physical systems and applications to traffic management. John Doyle will talk about universal laws and architectures and their fragilities. Sanjay Shakotai on resource allocation in wireless networks, and Wei Liu on deep learning to replace, improve, or aid CFD analysis in built environment applications. We also have a couple of exciting workshops coming up. One of them is being organized by Manya Gobadi and Muriel Medad at MIT, and it is titled Networks of Machine Learning for Machine Learning and by Machine Learning. So this will be a workshop at the intersection of networks and machine learning, networks meaning communication networks. And another workshop being organized by Costas Panos on the digital transformation of the built environment. So the first workshop I mentioned is in September. The one after that is in October. Please watch out for announcements for both. So if you miss any of the workshops or colloquium talks or research symposia, all of our events are archived on YouTube. So you can go to the C3.ai Digital Transformation Institute webpage on YouTube, and you can watch them at any time. The colloquium format will be, today the speaker will speak for about 40-45 minutes, and then there'll be a question and answer session at the end. You can use the Q&A feature to ask questions. You can upvote a question if you like, and we'll try to answer as many questions as time will allow. So without further ado, let me introduce the talk today. And the title of the talk is A Business Model for Load Control Aggregation to Firm Up Renewable Capacity. And the speaker is a giant in the area of operations research and energy markets. Professor Shmuel Oren is a professor of the Graduate School and the Earl J. Isaac Chair Professor in the Department of Industrial Engineering and Operations Research at the University of California at Berkeley. He's a co-founder and the Berkeley Site Director of PSER, a multi-university power systems engineering research center. He's been a member of the California ISO Market Surveillance Committee and a consultant to many private and public entities in the United States and abroad. He's well known for his research on nonlinear optimization, mechanism design, energy systems, and on the design and analysis of energy markets. He has a BS and MS in mechanical engineering from Technion and an MS and PhD in engineering economic systems from Stanford. He's a member of the US National Academy of Engineering, a life fellow of IEEE, and a fellow of Informs. So without further ado, I'll turn it over to Professor Oren. Please share your slides, Jenny. Yeah.
Let me turn here. Okay. Okay. I hope you all can see my slides.
Yes.
So I'm going to talk today about an example of how digitalization can help the grid and help the integration of renewables. And I want to start, I've been long enough, 30 years in this area, So I want to start a little bit taking you down memory lane. And basically, you know, this is taken out of the abstract by Fred Schweppe from his seminal 1980 paper on homeostatic utility control. And he already at that time envisioned the smart grid, saying homeostatic control is an overall concept which tries to maintain an internal equilibrium between supply and demand. Equilibrating forces are obtained over long time scale, 5 minutes, by economic principle through an energy marketplace using time varying spot prices. After that whole 80s, it was a proliferation of various technologies that attempted to provide the means for essentially implementing this idea. So here is a bunch of papers, you know, for people that think that they're reinventing demand response. Back in 81, we have demand side load management, trying to shave peaks of energy consumption by interrupting, curtailing different appliances during certain peak hours. This is a famous article by Art Rosenfeld back in 86 on smart meters and spot pricing, conducting a major experiment. The Electric Utility Week describes how by offering a menu of prices with lower prices having longer and more frequent interruption than higher prices. Southern California Edison had a very rich program. One of them was the interruptible service program where customers, based on the duration and frequency of interruption, they would get discount of their bill. And so as a whole way to manage or to introduce this product differentiation. This is one of my favorite, you know, for those of you who remember George Burns, he was the poster boy for a program on cycling of air conditioners. And this is describes the menu of, I don't know if you can, okay. It describes the menu where depending on the size of the air conditioner and the fraction of the compressor cycle that you are willing to subject to curtailment by the utility, you get payment that will reduce your electricity bill. This is one of my favorite plans in that area was called demand subscription. And the idea there is that each house had behind the meter a fuse, a way to reduce the size of the fuse or the amperage that flow into the house that was administered by sending a radio signal. This was the actual device. So you see they put something behind the meter, and when there is a shortage of power, the utility was able to send a signal that will trip the fuse to half its capacity. And by doing, and then they would send an earlier notification to customer that would light a light so the customer could disconnect certain appliances in the household to meet that load reduction. But they had still the freedom one day to watch a football game, the other day to disconnect the refrigerator. So behind the meter, they were in full control of how they use the restricted amount of energy that was flowing in the house. So this is just a picture, you know, people think that smart meters is a new thing. In '89, there was a company called Netcom that was providing smart meters to Southern California Edison that was functionally very similar to what we see today. So all these ideas were there. The technology wasn't as sophisticated as it is today and wasn't as cheap as it is today. But my contention is that technology was not really a barrier to implementing all this program. The problem was that we never came up with a sustainable business model that put end-to-end connection between what the customers are willing to do and how we're going to monetize that capability and reduce the, you know, make it available to the system operator. Now, what has changed since then is that now we have a much more prolific power systems with aggregators and flow in both directions and different renewables and batteries. And all these add a level of complexity that we didn't deal with it before. But in addition, there is all the big elephant in the room, of course, is the proliferation of renewables, which grow very rapidly. As you can see here, we are already at RPS 30% in California. And the problem is that the wind is highly volatile, unpredictable, negatively correlated with demand, which creates a problem. And then if you're talking about solar, we have what has become known as the duck curve. And what the duck curve, you know, if this is your normal demand, when you have solar, all the panels are getting energy, now suddenly the net load is dropping, and that creates big ramping at the beginning of the day down, and then ramping up at the end of the day. And that requires much more flexible resources that we normally had in our traditional system. So we have a lot of challenges. As I said, the proliferation of distributed energy resources, uncertainty and variability of renewable resources, all these pose new challenges to the system. And one of the ways to solve those challenges is by mobilizing flexibility on the demand side. Of course, there are other solutions. You can add more flexible generation, but if you're going to do that, you'll end up with a lot of gas turbines sitting at minimum load and waiting to kick in when the wind dies down. Or we have to develop new market design incentive for people to be willing to manage the resources in a more flexible way. And of course, there is all the smart grid technologies, especially storage, that is coming on the market, but storage is also very expensive. And it's much cheaper to try to mobilize the thermal storage in buildings and in refrigeration network and so on, which consume a lot of the energy in our society. And by managing the load and deferring it to hours where trying to follow the availability of the renewables, that's a much more expedient way of introducing storage than just putting a whole bunch of power walls. I'm going to focus on mobilizing demand response, which has been my passion for the last 30 years, and going to try to describe to you some paradigms for doing that. I want to add that another thing that is coming on the market, we have always to pay attention to the regulator, what the regulation is doing. And we see FERC introduced Order 2222, which essentially orders the system operators to create a niche or a market mechanism that will allow renewables to be aggregated and together with the demand response, and so the demand response will be able to participate in the market. Now, the general observation about demand response is that while today the metering and control technology is cheaper, technology was never really the barrier to implementing demand response. Unfortunately, a lot of people that are working on demand response and then and now are always focusing on the technology and trying to demonstrate that we can do it. And the technology is capable of providing that, and we can use the demand response to provide reserves and so on, rather than on developing business model that will facilitate the implementation. So I claim that the big barrier is now the regulation and the economics model and not the technological capability. The key element to making demand response a reality is that we need to have a regulatory framework that will enable it. And one of those things in the regulatory framework is to eliminate all kinds of subsidies that we currently have that disincentivize participation in mobilizing demand response, like feed-in tariffs for renewables, net metering for solar panels. All these are designed to incentivize the penetration of those technologies, but are creating subsidies that form a barrier to doing it the right way. We need institutional structure to implement those ideas, and we need a sustainable business model that will incentivize customer choice at the retail level and monetize those choices by producing valuable products for the wholesale market. Now, there are two major main economic paradigms for demand response. One is to provide real-time dynamic prices to retail customer. Some people refer to it as prices to devices. And the idea is that once you provide the right prices at the retail level, then Google will figure out a way to read those prices and to manage your thermostat in the right way, and the customer doesn't have to worry about that. This is kind of the economy's gold standard. Economists love spot prices, dynamic spot prices. However, my contention is that while treating electricity as a commodity works well at the wholesale level, at the retail level, treating electricity as a service may be a preferable approach. This is a classic debate in economics that has been going for the last 40, 50 years on prices versus quantities. And I say that I believe that at the retail level, probably quantity control is a preferable way to do it. This is reinforced by statements like this is something that I pulled out of an ISO Market Surveillance Committee report that say why there are many economists that are enthusiastic about demand response for all consumers. We are not aware of a reported success of real-time pricing for a big heterogeneous population area that could serve as a benchmark. Mobilizing retail level demand side flexibility to reduce operating and investment costs in the electricity sector by employing smart grid technologies and market mechanism is still regarded as work in progress. So the alternative approach that I'm going to advocate is to offer electricity at the retail level as a quality differentiated service. And we have all the technologies that to do that, we call them edge technologies. And to do that by signing contracts with customers that will accept load control options. The idea is that quality differentiated service and optional price plans are common in other service industry. When you fly with air transport, you can choose different kinds of service classes, different seats. Cell phones offer different type of price plans, would give you different service options. Insurance company allow you to choose your deductible. So this is something that that we are used to deal with. None of these industries offer to customers spot prices where they can choose on the spot how much they want to pay and how much they what kind of service they will accept. Those are all part of the service contract. So customers have experience of dealing with choosing between alternative service contracts. Now the challenge, of course, is that we need a business model and economic paradigm for the utility or third-party aggregator to bridge that gap between the wholesale commodity market and the retail service. Aggregated retail load control can be bid into the wholesale market for balanced energy, flexible ramping, contingency reserves, product or ancillary services. And we can do that in two ways. One of them is to have load control through direct device control, like controlling having an aggregator that has direct access to control your thermostat or air conditioning or water heaters or EV battery chargers. This is gives you fast response, and you know what you're getting. But some people may consider it a little intrusive to let somebody go, behind the meter and controlling your devices. An alternative, which is kind of analogous to what I described you earlier in California Edison, the demand subscription, is to have the control of power up to the meter, and everything behind the meter to leave it to the customer to control, either manually or by introducing some sort of Zigbee devices or other technologies. But anyway, the point is that the aggregator will only control the amount of kilowatts that flow into your house, and then the aggregator, the customer will control how do they want to use them at any point in time. Then what do you do with that? So the idea is that all these control options that the aggregators will buy from the customers through contracts are going to be put together into what we call virtual power plants, so that from the system operator side of that business, the system operator will see essentially something that looks to them exactly like any other generator, except that instead of burning, creating megawatt, it will be based on megawatts. This shows you some of the more modern approaches to doing that, to controlling the load and on the customer side. There was a company called Color Power, and their idea was to, when people buy appliances, along with the appliances, they'll buy like a plug that essentially assign the priority of service to the appliance, and then Color Power, through an algorithm in the cloud, is going to prioritize and control those devices, cycle through them, and harvest megawatts from through those curtailments, and sell it to the system operator by essentially creating a low duration curve or a price duration curve that they will provide those resources. This company, Color Power, has been acquired by a company called Zom Energy Networks, which I'm actually working with these days. And they are in the business of essentially mobilizing buildings and the residential houses and so on, by installing controllers on the air conditioners, or they can do it through a gateway at the building, high-rise building level. And for some reason, it's slipping through. And those units are going to be then again controlled through algorithms in the cloud that are going to harvest demand interruptions, so megawatts, and then form them into a virtual power plant that are going to be offered to the system operator to fill in the gaps created for ramping, or created by when the window goes down, and so on. This is what clouds offer. They have something called the Zom kit that is installed at different buildings, and they have already a population of customers that are signed contracts, and they already have experimental facilities that and the relationship with different system operator where they are testing that technology. Now, the other approach, which I described before, is which I call fuse control, where instead of controlling the devices directly, you can control the amount of power that flows into the household, and then you essentially allow the homeowner or the facility owner to decide how they're going to apply it. So the customer in this business will essentially assign segments of their load to different priorities, and which will be turned off or restricted under different conditions. And then these are going to then become the resources, and then the customer on the other end is going to be able to manage their appliances by deciding whether they want to keep the refrigerator running or whether they want to watch the Super Bowl. So this is the general idea, And this kind of tries to illustrate how we would manage that. So we assume that the household will have behind the meter maybe some solar panels and a car charger, and then they have all their appliances, and what they are going to get, they're going to, essentially the signal that they are going to provide is going to be the shadow price on capacity constraint, essentially increments of capacity, and they're going to get, I don't know why it's flipping, and then they're going to get the system, the aggregator is going to impose on them capacity limit based on their contractual agreement. So this is just, I won't have time to go through that, but we were kind of testing whether this is something that trying to simulate how a household will operate, and we can formulate a stochastic programming problem for the household, and you know, you can solve that. And I'll skip through to some of these slides quickly, but the idea is that you can develop a policy internally, how you're going to apply, how do you going to internally, how you're going to accept different constraints. And the result of that simulation is going to be that you can come up with a curve that is going to give you the shadow price for each household on each increment of the fuse, and that becomes the demand function that is going to be signaled outside. The key idea here is that this demand function is private information, and the aggregator is not going to have access to the demand function. All they can is interact with the house by offering a menu of service contract, and based on this demand function, customers are going to choose options out of that menu of service options, so that they will signal through mechanism design. You know, this is the idea of the revelation principle. They are going to signal their willingness to pay for different increments of the fuse through their selection. Let me go through quickly through so this is kind of the general paradigm that what we are describing, that you're going to have the household that interacts with the aggregator through, the aggregator is going to curtail the fuse size, then the household is going to choose out of a menu of service contracts. So that's going to provide to the aggregator a portfolio of curtailment options that they are going to put together and bundle it with some renewables that they may have in their portfolio, and they are going to firm up the renewables and then submit bids to the system operator that is going to then interact with the aggregator the same way as they will interact with any other generator by procuring megawatts from that virtual power plant. This is just to illustrate the idea of self-selection. Suppose that you have a kind of a different 8 customer types, and every customer, to make it simple, has a 300 megawatt, every customer type, but they are distributed differently based on willingness to pay or their interruption cost, if you wish. What's important to recognize here is that while the aggregator is going to interact with all these customers, they have to design a menu that is going to be applied to the entire population. To design this menu, all they need to know is the aggregate distribution of this willingness to pay. So in this particular case, you know, this is the total megawatt as a 200 megawatts with willingness to pay of $200 per kilowatt, 450 kilowatt, and 600 with 10, and so on. This is the aggregate demand function that can be extracted from the population through machine learning to some sampling. But the point is that the aggregator doesn't have to know what each customer preferences are. All they need to know is what the combined demand is, and then design a menu of options. And in this particular case, the menu of options that they're going to design is going to say to the customer, if you pay $84 per kilowatt per year, we guarantee you that this segment of load that for which you pay that amount is going to be interrupted with probability of 0.02. That's the highest reliability that you can get. If you only pay $72, you're going to interrupt you once in 10 years. If you're going to pay $48, we're going to interrupt you once a year. If you're going to pay $30, you're going to be interrupted 5 times a year. If you pay 12, 15 times a year. And if you don't pay anything, we're going to interrupt you 30 times a year. So we offer to the customer these options. The customer is then going to look at they have their private information about the cost of the kilowatt per kilowatt interruption, and they're going to add together the expected cost of the interruption plus the cost they're going to pay for the demand, and they're going to get this table. So each customer is going to optimize by choosing the minimum total cost, and the way we design the menu is in such a way that for kilowatt hours that are worth $200, they're going to choose the highest level of service. For this level of willingness to pay, they're going to choose that. So you see that we design the menu in such a way that the self-selection by the customer will automatically assign the reliability in order of priority as if we had the full information. This is the idea of the revelation principle that from economics, and that's how you design the mechanism. This is the illustrative example, and at the end of the story, you get that you have a distribution of curtailment options that customer have chosen that can be put together into a profile like that, and that becomes the resource that the aggregator is going to have that they're going to bid into the market. This is just a little bit of the math, how you design that. This is the very simple idea of mechanism design. And the idea is that we know if under efficient rationing, if we have perfect information, we know what reliability we can assign to each valuation by the customer. So what we want is that when we offer the customer a price for reliability, the customer will, the combined value of the expected service minus the price, the penalty that they're going to pay, when they maximize the net value, the net utility, they're going to end up with exactly what we would have assigned them if we had perfect information. And that's the mechanism design idea. So in general, what we are looking here at is that you are going to aggregate. Every customer has a distribution of willingness to pay segments, and then we put it all together, and we end up with an aggregate over the entire population. We design the contract based on that. So, as I said, the customer values a unit of consumption theta, which is kind of the type of the consumption, and faces a retail price of PR. So the outside option, in other words, the net utility to the customer, if it doesn't do anything, if it doesn't choose a contract, is going to be the valuation minus the retail price that they're going to pay. If, on the other hand, if they choose the contract, they are going to get compensated a price T, which is what the aggregator is going to pay them, in order to get a reliability of 1 minus R theta. And so the total utility that they get is R times their net utility, theta minus PR plus T of theta, and they optimize that. On the aggregator side, the aggregator owns some, let's say, variable energy resource producing S megawatts. This is the wind resources that they may have. They offer a menu of contracts to capacity increments with ex ante payment that vary with a customer self-selected probability. They commit, so they are going to commit now to the system operator to provide the quantity Q in the forward markets, and after observing the variable energy realization, they are going to dispatch a part of their by interrupting customers to make up the difference. So the total net revenue of the customer, of the aggregator, is going to be the wholesale price times what they commit to. And then there's going to be a penalty if they fall short, depending on the realization of the wind, or they're going to be a net benefit if they are get extra, but then what they're going to be paid if they get extra is going to be less than the wholesale price. So this is the general idea, and you can formulate it. This is a traditional newsboy problem, essentially, because what we are looking here is that the aggregator is acting now. It's the same kind of problem as you have when, let's say, airlines are deciding to how many seats to sell in each service category and how many overbooking, how much overbooking to do. They decide on the total capacity that they're going to sell. They calculate their total revenue, and then they take into consideration, if more under uncertainty, when the customers show up, if you have, they have to balance the probability that they're going to overbook against the probability they're going to have empty seat, and they solve this traditional revenue management problem. Here, we have a reverse situation. What we have is that you have all these uncertain resources on the supply side, and you have to decide how much you're going to offer to the system operator to provide out of all this demand, take into consideration all the uncertainties that are going to result from the wind realization, and maybe customers won't be on when you are interrupting them, and so on. So this is the traditional revenue management problem that we are solving. And just to illustrate the picture of the whole thing is that so the customer commits a certain amount of power to sell in the system. The aggregator commits a certain amount of power to sell to the system operator, which is going to be made up of the renewable. They're going to some demand side, and the balance they're going to have to buy on the spot market or pay a penalty for it. Then this is just a picture of how they're going to operate their demand response based on the realization of the wind. The aggregator is going to have to decide how many customers to interrupt based on the contractual agreement that they have. And of course, the more wind they have, the less customer they interrupt, but they're going to have kind of a policy region that you can derive. Just kind of the math, the way you design the contract is, as I say, you formulate the net utility that the customer is going to face if they get the service, and then you have two conditions that have to be imposed. This is the traditional design of contracts. One is called incentive compatibility, that says that basically we design the contract in such a way that when the customer decide how to reveal themselves or how much to subscribe to, they will have an incentive that when they optimize their utility, their incentive will be to reveal their true cost. And then there is the individual rationality condition, which says that when they reveal their true cost and they optimize their revenue, they're going to do better than not signing the contract. So those become constraints on the optimization that the aggregator is going to do when they design the contract. And that, there is a mathematical formulation that is going to be have to be solved. Just a simple illustrative example here is that if you, for example, if the wind is uniformly distributed and the retail rate is $30 and you have 100 megawatt of customer, and then we're assuming that the valuation that we have a uniform distribution on the wholesale price, what we end up getting is that we get two curves. One is going to be the probability of curtailment as a function of customer type. The other one is to be the price, the compensation as a function of customer type. Now, as I said, the customer type is actually, or the load type is private information. But the aggregator doesn't have to know that, because out of that, you can extract the data, and what you end up with a curve that offers to the customer a payment as a function of the probability that they choose. So this is the menu that is offered to all the customer, and the customer is the only one that knows what his type is and chooses the right point on this curve based on their type. One of the important things in this curve is you see that if the aggregator knew exactly what the valuation is for the customer, they would only pay them that amount, because this is the valuation that the customer assigns, so you only have to pay them epsilon above that. The problem is that because the customer type or the load type, the valuation is private information, the aggregator has to offer them more. The difference between the actual valuation to the customer and what the aggregator is offering the customer is called the information rent. And this is the typical result from mechanism design theory, that you have to pay customer much more than their actual valuation in order to induce them to reveal their type, and that's the information rent. So anytime people solve the problem and they assume that they know what the utility of the customer is, they're ignoring that fact that you have to pay information rent to actually know what the customer is going to do. And if you solve all that, you end up, as I said, with a supply function that is going to be offered, and this is going to be, in this particular case, the supply function that is going to bid into the system operator. And there's a paper that, if you want, in Journal of Regular Economics that describes all of that. Now, one of the things that I want to emphasize, and again, I have just a few minutes to go, is that in order to implement all that, we need some regulatory changes. The idea is that renewable resources must have incentive to firm up their supply. And today they don't, because we have feed-in tariffs that essentially don't give them any incentive to provide more firm supply. The feed-in tariffs is an implicit subsidy that doesn't charge renewables for the uncertainty that they create to the system. And this is something that will have to change in order for the renewables to have an incentive, and we're moving in that direction. On the demand side, again, we have all kinds of subsidies like net metering and so on, that doesn't give the demand, or volumetric meters charges, that doesn't give the demand the incentive to try to actually monetize the flexibility that they have. So we will have to have some regulatory changes that are going to reduce the subsidies and create so that people will have incentive to do the right thing. And this is something that has not happened yet. Now, just before I finish, I want to give you the epilogue of the whole thing. ARPA-E, just a year ago, decided, under the leadership of one of my former students, Corey Hedman, they created a program called Perform that has focused on trying to recruit, they gave 10 contracts, $30 million to different universities and entities to encourage this idea of allocating. Essentially what we are trying to do here is to distribute some of the delivery risk down the supply chain and to let customer bear part of the risk. So this idea of risk management and distributing the delivery risk down the supply chain has been formulated into this program, and there are different projects going on. I teamed up with some of my old colleagues, and we got a contract that is doing just that, and essentially in the process of trying to implement some of the ideas that I just described at PJM. So what we are doing here is ZOM network is going to provide the technology for the customer curtailment. And then the idea is that we're going to create those virtual power plants that we are going to bid into the system operator, and as I described to you before. My zone technology, this is essentially it's already a working technology as I described. So those units are already placed in multiple buildings, and we are now in the process of trying to simulate and trying to implement this idea with people at PJM. And my colleagues here that I've been working with for many years, this is Alex Papalexopoulos, who is the CEO of Zone Technologies, Hank Pochau, who was the product manager at EPRI when I started to work on this priority service, and then Robert Wilson, who got the Nobel Prize in Economics this year, and he was one of the team members at EPRI many years ago, and we've been working on that. So tune in, and hopefully in a year or two, we're actually going to have a working model of this. Thank you.
Thank you very much for the nice talk. If the audience has any questions, please post them in chat. There is one question from Caston Day. One form of demand side response I know is using home heat energy as a battery. Example, run AC only overnight, not during peak hours, thus treating the home as an energy store. Is this viable in your eyes?
Yeah, you know, I mean, I actually even have a paper with some people in Denmark, and we were looking, not quite that, but the idea was on a larger scale to have for some of the refrigeration system at supermarket chains to create ice tanks adjacent to the refrigeration, and at night to basically create ice, and then during the day to reduce the consumption of power by running the air over ice. So this is kind of similar to what is being described. I think that this is the idea of having ice makers part of your air conditioning system, or having or maybe overheating your allowing your water heater to overheat during low prices, or when there is abundance of electricity, and then run it cooler when there is not. This kind of ideas is exactly what I'm saying, that there is all this potential of heat storage and managing when you're going to managing the consumption of electricity in those heating and cooling devices is one of the best resources that we have, and it's going to be much cheaper than buying Tesla batteries.
Thank you. If there are no other questions, I have a question. You mentioned differentiated service.
Yes.
I've heard that in some states like Texas gives you a lot of different plans. There are some parts of Texas, people have many different plans and they can choose from them. Is that already like differentiated service, or what is that different from what you have in mind?
Yeah, well, Texas started, I used to consult in Texas for many years, and Texas started by allowing retail energy providers, and effectively more than 50% of their load is now supplied by 60 retail energy providers. The emphasis there was more, since this started way before we had all these edge technologies, the emphasis more was like when you choose whether to buy a fixed mortgage rate versus a variable mortgage rate. It's more managing the payment than managing the devices. The emphasis was on that those retail energy provider are going to buy wholesale power, but they are going to give the customer, they're going to essentially provide the customer a mechanism to hedge the volatility of the wholesale price, because the wholesale price in Texas can go all the way up to $9,000 a megawatt hour during shortages. And we saw what happened last February there And the retail energy providers specialize in exactly what kind of hedge. They give customer a choice how much of they want their payment to follow the wholesale price versus how much they want to more have a stable fixed price. And there was one company that was called Greedy, that they actually offer customer the opportunity to just follow the wholesale price completely. And they ended up, those customers ended up stuck with prices of $17,000 a megawatt hour during those days when there was the price freeze. So they were the Greedy was actually kicked out of business. The argument was that customers, I don't think that they should have been, but the argument was that they didn't provide enough information or enough training to customer to be able to handle that kind of uncertainty. But that's where the emphasis is. When I'm talking about differentiated service, I'm talking about allowing customer within their household, not just to choose how much they want to follow the wholesale price, but to actually use behind the meter technologies to divide their load. So under the paradigm of differentiated service, instead of having to curtail customer the way they curtail them in Texas during the cold snap, that you cut them completely out, we would have the technology to be able to reduce customer instead of 8 kilowatt to 2 kilowatt, so that instead of curtailing people completely, each of them will have the minimum amount of energy for what they really need, for their artificial lung or their, dialysis machine. But maybe they won't be able to run their freezer in the garage. So the idea of using edge technology to differentiate service is to allow customer to buy, to be, in case of emergency, to be curtailed part of the way instead of being curtailed completely. And then instead of some people being curtailed completely and some people not, to be able to curtail everybody maybe to 20% of their load so that nobody will freeze. And that's what we don't have yet. And it's unfortunate because we do have the technology to do that. And we do have the mechanism, the economic mechanisms to try to deal with that. So, if we're going to digitize, to have digitalization, that's one good area to apply digitalization.
Thank you. There is a follow-up question by Castan Day, but I think you might have answered this. It says, do you think energy subscription business model is the right idea for only industrial customers, or would that work for residential too? I think you're also suggesting for residential too, right?
Yeah, I suggest it for residential. The difference is that, for big industrial customers, they can do that and deal directly with the wholesale market. For residential customers, we need this, we don't have the way now, maybe under 2222, we are that, it's not feasible for the system operator to have to deal with with millions of customers and kind of manage their load. So what we need is these intermediaries, those aggregators that are going to create those portfolio, sign contracts with many customers, and then pull them together and, kind of multiplex through customers so that you minimize the hardship by cycling through and not interrupting everybody's air conditioner completely, but maybe interrupt everybody's air conditioner for 5 minutes and cycle through 1 million customers. Then you can harvest enough energy and the customers will hardly notice. Maybe the temperature in their house will go up 1 degree, 1 or 2 degrees. So what I've been proposing is essentially a way, by creating this virtual power plant, a way to be able to make that kind of subscription also accessible to customers, private, small customers.
Thank you. I think we are near the top of the hour, so let me thank you again for a very nice talk. And thanks to the audience for attending it, and I hope to see many of you for future colloquiums. Thank you. Bye.
Thank you very much. It was a pleasure.